Our next speaker is Claus Ekstrom, who's Professor of Biostatistics at the University of Copenhagen, and he's going to be talking to us about the inevitable statistical problem with overdiagnosis. Okay, session.
Right, does the microphone work?
Nope.
Say something again, Claus.
So does the microphone work now?
I muted it. Turn off the mute.
Turn it off the mute.
Does it work now? Yeah. Let's see. Right, so thank you very much for inviting me to give a talk here at the conference. I'm a statistician and I normally work with omics data. So genomics, metabolomics, whatever omics that you would want to look at. So in some sense, that is the world of big data. Statisticians don't like the term big data, so we usually just call it data. but since that's a term that is often used, I'm going to I forced myself to put it into the slides. I don't like it, so just read it as data. Right, so a statistician is usually concerned about risk. And what you may not know is that yesterday we were all at very great risk of having a nuclear meltdown in this very room. The reason I'm saying that is that when we talk about overdiagnoses, we have individuals and we want them not to worry. And that was the same with all of you yesterday. We didn't want you to worry, so we didn't tell you anything about it. But there was a problem with large risk of nuclear meltdown. And if we go back, say, to last millennium, what were we supposed to do if we had a high risk? So the thing that, if you're all like me, that's the original Ghostbusters, the true one from 1984. You know, when you see the movie, the beams are not supposed to cross. That's what they're told. You're not supposed to cross the beams. And what you don't know is that in this very building, yesterday from 9 to 6, there was a conference about initiatives to start whole genome sequencing on all Danish newborns. I snuck out from this yesterday morning. I went there, I'm sorry about that, for 2 hours and listened to a couple of the talks. Here's the presentation, overview of that. And I am sure that if one of the presenters from that talk had been in this room, you would have stood with torches and pitchforks and lynched the person. So the problem is, of course, that they have all of these nice data and they want to do a lot of good and they don't worry about overdiagnosis. They say it. Oh, shouldn't we worry about overdiagnosis? Everyone says yes. They don't know what the definition is about overdiagnosis. This is something that is coming in Denmark. Every newborn will have a full whole genome stream. Okay, it didn't happen, the beams didn't cross, we're all alive, we can go on and be happy. That was the point. Okay, so here's a quote that we often hear. So if we have enough data, and that's, some of the people argue a lot about us being able to collect a lot of data, hoard big data in some sense, is that as long as we have enough data, the numbers will speak for themselves. So that's not true. And I love data. I've worked with data all my life. I feel myself as a kind of detective trying to figure out what's going on. And the problem is that statisticians have been trying to figure out how to extract information from data in the last 200 years. And it's not becoming easier because you have more data, it's becoming more and more complicated. And just collecting the data and holding it is not making it easier, and it's not helping with the problem of overdiagnosis. About 400 years ago, Descartes said that man is a machine. We just, the body is a machine, and we have the soul, and he didn't talk about the soul, so just the body and the machine, and once we know everything, it's all deterministic. That's clearly not the case. And another thing that is not the case is that the data doesn't speak. The data doesn't tell us anything. We can only extract the information if we use the data in the right context. Let me show you an example. So here's a very old illusion. There's an old woman there, there's a young woman there, maybe there are two women there, and maybe there's nothing there. So if we know that we're supposed to find the old woman, the majority of us can do it. If we know that we're supposed to find the young woman, most of us can do it. And we can even swap back and forth. Some can even see it at the same time, which I think is slightly complicated, but anyway. But the problem is all the data is there, but we only know what is the stuff that we should extract if we know the context. And that is the main problem with all the big data approaches that are being used right now. We're just collecting the data, and we are 1 or 2 lengths behind figuring out how we should analyze it and extract the information. But we're still collecting and using that, the notion of just getting the data as the reason for doing all of this. Okay, so on the left of this slide here, you see 4 promises that are often given with big data. We are able to get absurdly accurate results because once we know everything, it's just a matter of simple computations. And it's possible to get everything. Henrik showed you a couple of the technologies that can be used to measure sweat or blood or particles in the air, whatever. And we have all the omics information, the genomics, proteomics, and so forth. And we'll just go ahead and measure everything that possibly is. And then we don't need to worry about the statistical modeling. We don't need to worry about causality because we have so much data that we can just look at the correlations. And if there's something that we know by now or should know by now, is that we shouldn't just look at the correlations because the correlations doesn't really tell us anything about the system that we're looking at. They only give us patterns, and those patterns could be true or they could be false or partly true or partly false, but we don't know. And we need the causality approach to try to figure out what's going on if we want to apply this on real people. So I'm working mostly in genomics, and some of the arguments that we see is cheap to collect. $500, I think, was the value of the whole genome sequence they mentioned yesterday. That's not too bad, and they are stable. We just need to collect it once, and we have it for the rest of the life of the individual. So no need to measure again in some sense. It's likely, so we know a lot of diseases have a genetic component, so it's likely to have impact on multiple phenotypes or diseases. That's very nice. So we get a lot of information for a small amount of money. And that is true. And there's a lot of possibilities in big data, in omics data, and not just in genetic parts of data, but also in environmental data, which people who work in genomics, they don't talk about that because they just see everything as genetics. But obviously there's a whole bit of environmentability as well going on, but it's so promising with what we can do. The thing with genomics is, of course, that the SNPs mutation, the mutation in the SNPs, or the DNA sequences, that is so far away from the end result, the patient, the phenotype. There's so much going on, there are different levels of molecular biology going on, time, environment, and everything else. So the predictability that we get from those SNPs is not really that good. Henrik showed you a couple of examples of that, and it's not really getting better. They've been doing this for the last almost 20 years, and if you talk to them about what have you really learned, what has this mattered to patients, it's not that much. And that's the type of data that we want to use. Okay, so the problem with big data is there's really no definition of big data, and you probably know this claim here. We know it's good, so that's why we should be doing it, big data. And also, we know that once we have all these data, it must be better. We have all the data, it must be better, but it's just more complicated. So let me give you some examples of the way that we're using big data to try to address overdiagnosis is giving us a lot of problems right now. Okay. So these are the items that I want to go through. So we have larger samples, better coverage, more variables. We have, hopefully, big data will give more precise diagnoses. We can get earlier scans, so we know by birth or earlier when we actually need to start treating individuals, or at least be aware of them. We can look not just for a single item or a phenotype or outcome, but multiple at the same time. We should look at lifetime trajectories, and then possibly we should redefine the disease definitions. So let's look at this. Okay, what goes on if we have large samples? And large samples, I mean both that we have a lot of variables, so that's the P year, that increases, so we are measuring just about everything we possibly can of these individuals. But also that we have a large number of individuals, for example, the whole population. So if we are actually going ahead with the newborn whole genome screening, then in 30 years, for example, we will have the full Danish population in some sense. So that number is going to be massive as well. So the problem, of course, is once we increase the number of things that we measure, we are likely to get the things that matter. And that's the lure of big data. But we're going to get a lot of other things as well that we need to remove. And the problem is we are including much more noise in the system than we are including signal. And there are no ranges on the axis here, or at least not on the y-axis, but notice the form of the graph. So you can show mathematically that this is the relationship that you will have with the signal to noise ratio, so you want the curve to be high, and the number of features or the comparisons or the number of variables that you measure along the x-axis. It drops insanely quick. So that means we have to collect a lot of data, and then we have to figure out to remove most of it to be able to come back to the signal. Removing most of it is not a trivial problem. And that is one of the caveats with the big data. So we're collecting all of that information, and extremely quickly we are losing the signal in all of the noise. It can be fixed to some degree, but only to some degree. Another problem that we have with this type of data is that once we have reduced the data that we have available, we have made a model, we can probably get 100 different models that are just about as good at predicting the outcome. So how are we going to use that information if I need to have shoe size and hair color to predict my risk of overdiagnosis for one model, or maybe I need age and whether or not I had a banana yesterday to predict the same type of overdiagnosis for another model? How are we going to use that information to treat the patients? Maybe we can predict who's going to be overdiagnosed or not, but we don't know why. And that's what we want to aim at as well, not just the diagnosis or the overdiagnosis. Drops insanely quickly. So maybe what we need to do if we want to look at more precise diagnosis, and that is the word of the town yesterday at the other meeting. It will be more precise. So if we look at statistics 101, I think you could call this, most of you will have heard about the positive predictive value. If I have a positive screen or test, what's the probability that I will have the disease? So that's the definition that we see here. Notice the last line here. Let me see if I can. Yeah. So what we have here is the sensitivity and the specificity. Those two terms enter in the calculation of the positive predictive value. What they're talking about yesterday at the other meeting is fixing the sensitivity, making it bigger, fixing the specificity, making that bigger as well. They don't care about overdiagnosis, or maybe it's not that they don't care, they don't know it. They think it's the same thing. And we've been hearing that throughout today and yesterday as well, that a lot of people, also our colleagues, researchers, they don't really know what this is. They are happy because they're trying to fix this and fix this. So we need something more than this, because that's not really the point of interest from the patient. So let's define a new term. Henrik had a lovely new term BOP data. I'm so sorry I didn't invent that. That was wonderful. So I came up with the honest positive predictive value, slightly more boring. So it's not just if I have a positive test or positive screen, what's the probability that I actually have got the disease? It's the probability that I will have the disease and that it will give me problems. So let's go through the math on this. Now, we're going to spend a lot of time on the mathematics, but we can write it up in the same way that we could write up the definition of the positive predictive value. And we can actually work through the different terms of this formula here. I'll just show you what this means. So here we have the probability that it's a problematic disease, given that the screening was positive and we truly have the disease. That is 1 minus the risk of overdiagnosis. Here we have the positive predictive value. Here we have the probability that I will have a problematic disease if I don't have the disease. That's going to be 0. So I don't have to worry about this one here, and I end up with this very nice formula here. So the honest positive predictive value is the regular positive predictive value scaled down depending on the size of the overdiagnosis. And what everyone is modeling is this one here. So imagine that we have a positive predictive value, I'm just inventing numbers here, so say of 80%. And we can improve the positive predictive value to 85%, or maybe 90%. That's going to be nice, but that has a very small impact on the overall product of those two, because if the risk of overdiagnosis is big, 20%, 30%, whatever percent, then a small change in percentage points from 80 to 85, or from 80 to 90, has no impact on the overall risk of individuals. So we need to work on this bit here. And of course, all of you know that, so I'm preaching to the choir. I didn't dare say that yesterday at the other meeting. But we really should not just model this part here, but also model the other one, or the combination of the two. Right. Then Henrik had this presentation of this paper that came out last week, or the week before last, on where people aggregate, well, the authors here, they aggregate the information from a lot of genetic risk scores to produce a polygenic risk score, and using that to look at 5 different outcomes, diseases, and classify individuals as to whether or not they are at increased risk of getting this disease or not. And they validate it in another study, and everything is fine and dandy. They don't look at overdiagnosis, as Henrik told you. Not at all. So they mentioned that what they think is important here is that they have something that is clinically significant, let me see, increased risk. Clinically significant increased risk. I don't know what that is, clinically increased significant risk. Is there a number we need to go above before it's clinically significant increased risk? It's a relative risk. It's actually an odds ratio that they're looking at. And if you studied epidemiology 101, you know that you shouldn't really look at relative risks. You should look at it if you want to figure out if something is working. But if you want to figure out, does it have an impact on the population, you want the absolute risk. They don't mention that. And also, they validate their model based on area under the curve. And that is okay, but it doesn't say anything about how well the model is predicting. It just says, if I have something from the low risk group and someone from the high risk group, will they predict the high risk group person having the higher risk? Yes, it will. It has an area under the curve for 0.81. But we want the calibration curve saying just we actually hit the risk that you're predicting. Not just if one risk is higher than another risk, but are we getting the risk that you're saying that individual has? They don't do that. So we have something that's saying, oh, we have all these wonderful results from big data. It doesn't help us anything at all with overdiagnosis. Probably it's going to worsen that. And it may even redefine what we talk about when we talk about disease. Now it's not disease, now it's increased risk of getting a disease. So increased risk is a promise that you might be ill at one point, but But is that really what we want to use when we want to give the information to individuals about what is going to happen to you? Okay, multiple outcomes. So if we screen for everything, we have all the information on everyone, we have a number of features that we could screen for, that is along the x-axis. On the y-axis, we have the risk that a person will be overdiagnosed at least once. So let me just go through this. So here we have different risks of overdiagnosis. So for the blue disease, so I have one type of abnormality down here, and if all my abnormalities have a risk of overdiagnosis that is 5%, that's probably very low. We can see as I increase the number of abnormalities or diseases, diagnoses that I run through, we can see how this risk of getting at least one type of overdiagnosis increases. So this is for a 5%, the green one is for a 30%. So imagine that there's a 30% risk of overdiagnosis. If we're just scanning for 5 different things or screening for 5 different things, we have an 80% chance of being overdiagnosed for at least one of them. The critical part here is how steeply these curves, they grow. I mean, we have 5 abnormalities or risk genes or whatever. We also have 20. So if we just act on the size of the risks or the results that we get from these early screenings and start treating, and then we will all be overdiagnosed with at least one thing, possibly more. So this is an old result. The important thing is how quickly this actually goes towards 100%. It's extremely quickly. And these are low risks of overdiagnosis. Right. Another issue that is being discussed is the use of lifetime trajectories. So if we measure everything on everyone at every time, then one possibility is to try to figure out when is a person getting a diagnosis. So we have one person, we have 3 persons here. So the first one at this time here gets the diagnosis X, and sometimes time goes on, and then that person will get the diagnosis Y. And we have another person at some point in time, that person gets the diagnosis G, and later on E, and so forth. So when people talk about the use of big data to try to figure out something out about lifetime trajectories, this is actually a good idea. It's not working at all for overdiagnosis, but this is what they're doing. And actually, there was a major research grant given in Denmark, I don't know, maybe half a year ago, whatever, where they want to look at exactly that. So figuring out by using the Danish registries, when does each individual get a specific diagnosis? So can we predict what is your pattern, like beads on a string, of diagnosis throughout your life? Nothing at all about overdiagnosis, at all. So it's just what do we have registered for that particular person? Does it matter or doesn't it matter? And one thing that is good about this is, of course, that we don't just suffer from a single abnormality or disease. There's a combination that's going to influence us through our lives. So we really want that pattern of what is going on, but we want that pattern also to reflect what is actually being done and how is that influencing the individuals. So a lot of approaches on how big data are being used right now to try to model diagnoses, and none of them try to fix the problem with overdiagnosis. So if I'm going to take on my statistical glasses and say, what should we be doing? Instead of looking at what we're doing wrong now, what should we be doing? What we really should be doing is starting to model overdiagnosis. Going back to the honest, positive predictive value, it's not enough that we model whether or not you have a specific disease. We need to figure out if you have a disease that is relevant for you. So we need to redefine the outcomes, and Henry talked about that. We heard talks yesterday and also this morning, that we need something that we can use that is not just anecdotes. So whenever you talk to a GP, he or she will say, I have this case and there was this diagnosis, but it really didn't matter. And all of that is good. But if we want to do this in a large scale setting, we need to update the information about what is a disease. So when do you really have a disease? You don't have the disease necessarily because you have the diagnosis. So we need something else. And of course, what is going on in many situations right now is that you have the diagnosis, then you initiate treatment, and let's say that you figure out that there's not a problem. A lot of people would argue, well, the treatment worked. But a lot of those individuals also include people who are overdiagnosed. So we need the information from this group here as well. So if they had the diagnosis, they didn't get the treatment, and it was no problem at all. That group of individuals is difficult to get because of legal reasons. There's a system in place on how we actually initiate treatment based on different diagnoses, and we're not able to get that. So we need research that are able to focus particularly on this case here. And we've heard talks today and also yesterday where there were some good indications that a specific treatment was used. People found out it didn't work, the mortality didn't change, for example, and then it was revoked. All of that is good, but that is the low-hanging fruits. This is only going to work if we have the situation where the treatment might work on some people, but not on other people. And that is difficult. And we need a proper model that can try to handle that, and we need an outcome definition that everyone can agree upon. That if you have this particular combination, then you have the disease in the old definition of the disease, but it doesn't matter to you. So we need to update the disease as Henry talked about. And we haven't even talked about what's not a problem. So it's okay to say, okay, you have the disease, it's not going to be a problem for you. When is it not a problem? So we need a new classification of that, and you are the only people who can give us that new definition that you should more or less agree upon. Consensus, that's probably difficult. And also, we need something that can be used in a large-scale setting, so we can use the standard techniques for statistical analysis, including big data analysis, to use this to figure out not about the current definition of disease, but about a specific version of the disease where some of them are critical and some of them are not. Big data cannot help us here. Machine learning techniques cannot help us here. We need to have people to sit down in a room, across a table, and discuss this and figure out what we're doing. Here's the graph that Henrik also showed you. I'm just going to play the devil's advocate for a second. So Henrik quickly went through this. But if you're a statistician and you want to look at something like this, you want a loss function or a utility function or a cost function. So if we're going to talk about different definitions of diseases, diagnosis, what's the cost of choosing one type of classification for disease relative to another one? What's the cost of overdiagnosis? What's the cost of missing overdiagnosis or what false positive, whatever? We need to put a cost on the progress that an individual can go through. So remember here we're just looking at a simple abnormality, a single feature. So we need to put a price on a human life. A lot of doctors are not allowed to put a price on human life. If you're an economist in Denmark, the price of a human life is 32 million. So that's about 4 million euros. If the government needs to figure out if things work or not work, that is roughly the price, 32 million. So what's the cost of overdiagnosis? We need to put a number here. We need to put a number here. And for all the different possible outcomes, we need to put a number. What's the cost of screening? And until we do that, we are going to end up in a discussion where some people are saying, oh, we are improving the risk of successful screening and treatment, and other people saying we are improving increasing the risk of overdiagnosis. We need to put numbers on it, and it's not a fun job to put the numbers on, say, this is going to cost us so much in quality of life, or Danish krone or whatever, and then we can optimize the full system and figure out, okay, if we have all the information from all the data with the new classification, what is the cost going to be if we screen everyone? If we only screen some people, if we screen individuals that have a risk that is increased by threefold or whatever. And we need to have that in order to be able also to compare different definitions of disease. So as Henrik told you, we have different classifications of disease, that is over here. But if we have two different classifications, then we can just use those two different classifications and compute the overall loss and figure out if one is better economically, or figure out if one is better in quality of life measures, and use that as a way of guiding our approach to defining when is overdiagnosis a problem, and when is it a big problem, and when is it not a problem. And that's just for a single outcome. We have another problem, and that is timing. That is very rarely discussed. Timing is complicated, because we don't have the diseases or the abnormalities from birth. The majority of them we get during life. So, as my mother likes to say, you can only die of one thing. I'm not sure if that's true. But in some sense, you can only die of one thing. And in that sense, when we talk about overdiagnosis, and overdiagnosis in large-scale data sets, we need to have multiple outcomes and the timing included. Because we have, if you don't worry about overdiagnosis, but just at risk in general, then you have the statistical model for competing risks. And competing risks can handle the different types of outcomes, and once you've died from one, you cannot die from the other, and so forth. And we need to have something that will accommodate the same result, but for overdiagnosis, competing risks of overdiagnosis. If I'm highly likely to die from something in the next 3 weeks, should I worry about something else? Probably not. But if I don't know that information here, then I might have to worry about the why. So it's not just a single thing. You need to have all the outcomes and a model that can accommodate it and will address the overdiagnosis. Okay, so 3 steps for improving the modeling. We need to look at better definitions. We need to have timing in order. We need maybe to have a loss functions that can make our classifications better. And the last point I want to make is that we need to cross the beams. And we need to cross the beams and talk to the people who are sitting 4 doors down in another auditorium and driving all the technology because they love it. They love the technology, it's new, it's good, everyone would want a piece of this new technology. And if we cannot hammer the problem with overdiagnosis into their heads, we are going to have a problem. So we need to build that bridge. Thank you.